Okay, here is a practical looking at phenomena Young's slits and effectively what we have. And there's a theory video to explain this better, so that would probably be worth looking at first. But essentially we're going to have and this is grossly overdrawn, there is two tiny slits in a bit of plastic. I'll actually show you it. It's looking like this. Very, very tiny, very small two slits, which we're going to set up, behind which we're going to place a laser. The laser, of course, is going to produce light. That light, which is coherent, strikes these two slits at the same time. And then much further down here, we have a screen in which we're going to see bright, let me write bright first, and then dark patches. Bright, dark patches. I've done dark in the pen. Dark, bright, dark. And the theory basically suggests that you can predict the width of the bright patches to the bright patches, so long as you know the slit separation, you know the wavelength of light that's inbound, and you know the distance that the screen is away from the slits. And the equation is quite simply, and once again, if you want to look at the theory for this, then go to the theory video, which I'll put down below. W equals lambda over S, D. Good. So what we are going to do in this experiment is we're going to look at how we're going to change, we can't change lambda, we're going to keep this constant. We're going to look at a set slit width, and then we're going to alter D and look at how the width of adjacent bright patches alter. So our independent variable is going to be D, so that's the distance of screen to slit, and we want that very large. The theory video described why we want that very large, so it's going to be in the meters. We're then going to look at the width of adjacent slits, and that is going to be incredibly small, and that's going to be in millimeters. And because it's incredibly small, it's probably worthwhile not just measuring the width between one, but the width between many. So we're going to do 5 adjacent slits here. Obviously, this is the dependent variable. You're going to look at that once, twice, and an average, maybe even 3 times, but I think 2 should give us something credible here. And then, of course, finally, the width of adjacent slit in millimeters by merely dividing this average by 5. So there is the table of our results. It seems a very straightforward experiment. The problem is how small this value is. So therefore, in order to make that as large as possible, we want to make this as large as possible. So we're talking about large distances. And also, it probably requires a vernier caliper to measure that separation, because remember, a vernier caliper is accurate to 0.01 of a centimetre or 0.1 of a millimetre. Okay, let me just take you to show you the setup of this experiment. Okay, here is the setup of my experiment. What I have here is I have a laser that's mounted, and then that laser is shining towards the double slits that I showed you earlier. You can see the little red dot sitting on the double slits, because that's showing that it's being illuminated. And then, in the very far distance, and I'm going to, well, first of all, let me show you, because I'm going to slowly move us down so we can see what's happening here. We have, those is a meter ruler here. We're interested in very long distances. So we've got this tape measure, and that's going to measure the distances to this screen here. And I'm not sure whether you can see that perfectly. So what I'm going to do is I'm going to turn the lights off in a minute, but there are a series of bright and dark patches along there. Let me turn the light off. See if we can see that slightly better. Yeah, a series of light and dark patches. And what I'm going to do is I am going to draw on the screen with my pen where those light and dark patches occur. Let me turn the light back on to show you that. Let me see if I can focus again on there. Now I can see this just about. And what I'm going to do is I'm going to put a little marker, and then obviously the finest marker you can do, and then I'm going to count 1, 2, 3, 4, 5, and I'm going to put another marker in there. So I have these two very small pen lines, and also I know this is running at, that's 1.10 meters. That's why I positioned it as I have. And so what's probably next best is that if people then try and take the width separation with a vernier caliper. So this can be removed altogether, and then you can get different people to start measuring the separation of those two with the vernier caliper and the vernier scale, which, if you're confused as how it works, I'll show you another video on how you can get the value for that. However, this is probably the best way in which to work out the separation. And then you can either move this one back to another position, or indeed you can have another one set up further down, and you'll probably notice here it's a long way down at 2.70 meters. But the reason why we want to go to 2.70 meters is because the separation of the fringes is so much greater. If I've got one there, 1, 2, 3, 4, 5, we've suddenly got at 2.70 meters a much greater separation, and so therefore it's much more likely to get an accurate result. Let me turn the light off one more time so you can see that. So you can probably now start to see those individual fringes much more easily. Remember, it's the individual little lines. It's not this gap here to this gap here. It's those individual lines that you're most interested in. Okay, let's go and take a look at some results. Good, so having got all these individual whiteboards, you can now, you can then measure those separations. Let's go to the next one. And then, from there, start to compile the table of results. And you can get more than one people to do it, or you can just get more than one people to attempt to measure the difference, because vernier calipers are really tough to use in the first place. Okay, there's the table, and of course this is now the table of results. And nothing profound to see here other than making sure that we have the accuracy required for millimeters, and vernier calipers can give you the to a 0.1, though probably our biggest problem is going to be how large that marker pen is. But nonetheless, got to keep that consistent. And then finally, what are we going to do with the data? Well, 2 more bits of information required. The separation of the slits was 0.4 millimeters, and that was given on the material, given on the that little slide. It's very hard to measure that one, so it's probably best to find a known one. And then what we're going to do is we are then going to plot a graph. Remember, the independent, what you changed was the distance, which is in meters, and what you measured was the separation in millimeters, or indeed times 10 to the minus 3 meters. And then when you plot it, you should get a nice straight line. If we are happy that the equation is W is lambda over SD, then y equals mx plus c. What you've got is y you've plotted there, x you've plotted here, so therefore the gradient should equal lambda over S. So if you work out the gradient, you will be able to work out the wavelength. Now the gradient, bearing in mind, has a 10 to the minus 3 here, so you need to make sure that the two values there are 10 to the minus 3. But if you multiply that by the separation, which we know was 0.4, and 0.4 millimeters, 10 to the minus 3, that should give you the wavelength of light. And as you noticed, we were using red, which is approximately 700 to 660 nanometers. So give that a go and see if that comes out. Okay, hope that makes sense.